In the previous video, we decided to use Gaussian mixture model to fit our data set and to solve the clustering problem. But how? How can we do better than the general stochastic gradient descent? So in this video, we will discuss some intuition that leads to expectation maximization algorithm for this particular case. Okay, to recall that the density of each data point in our Gaussian mixture model is a weighted sum of 3, or in general as many as you want, Gaussian distributions. And to start with, we will need to introduce a latent variable here, because it will make the reasoning about our model much easier. So what can we call a latent variable here? Well, we can do something like this. We can say that each data point was generated by using some information from a latent variable t, which exists, like we have one latent variable t for each data point x, and it causes x, so it explains something about x. And the reasonable thing to assume about t here is that it takes 3 values, 1, 2, or 3, and it shows us from which Gaussian this particular data point came from. So we actually don't know, for any data point, we don't know from which Gaussian it came from. So it's a latent variable, right? We doesn't observe this never, nor in training, nor in testing. But this can be helpful. So if we know the latent variables, it can be helpful to understand something about our model. And later, then we feed the Gaussian mixture model into our data. We may find the distribution on the latent variable given the data. So we may ask our model the question, how do you think? What is the value for the latent variable t for this particular data point? And the answer to this question will be basically the clustering, right? It will gives us the belief, like from which Gaussian this data point came from. So if we decided to use this kind of latent variable model, then it is reasonable to assume that the latent variable t has prior distribution pi. So it's exactly the weights of our Gaussians. And the latent variable t equals to some cluster number, for example, 1, with probability pi1. And the likelihood, the density of the data point x, given that we know from which Gaussian it came from, is just Gaussian distribution, because it came from the Gaussian. So each data point, if we know that it came from the Gaussian number c, its density just this Gaussian density with the parameters of the Gaussian number c. Okay, when we introduce this kind of latent variable model, we may now look at what will p of x given theta represent in this model. So we change our model, and we now have to check that it still gives you the same general results as our original model. If we write down p of x given theta given parameters in this latent variable model, we'll get this. It's just a sum of it's just a rule of sum for probabilities, and it says that p of x given theta equals to sum with respect to t. So we are marginalizing out t. We are summing with respect to all possible values for t, from 1 to 3. And we are summing the joint distribution p of x and t, which equals to the likelihood times the prior. And if you substitute the definition of the prior and likelihood into this summation, you can understand that this last formula on this slide is exactly equal to the first formula. So we introduced some latent variable in such a way that when we marginalize out this variable, we get exactly what we had before. Which means that we now can use this latent variable model, train it with the observed data x, and it will give us exactly the same results as we would get if we used the original model. So let's now try to build some intuition about how to train this latent variable model. So say we have a data set, and now say it's one-dimensional. So each data point from 1 to n is just one number for simplicity of illustration. So our goal of finding the maximum likelihood estimation is finding the parameters, right? How can we find the parameters? Well, it turns out that if we know the sources, if we know the values of the latent variables for each data point, then finding the parameters mu and sigma is easy. Because, you can say that all the blue data points here is the data points for which we know that they came from the first Gaussian. And we can look at them separately from all the orange data points and just fit them into one Gaussian, which we already know how to do, because it's just fitting some data set of blue points into a Gaussian distribution. And you can look, you can see the formulas on the bottom of the slide, but it's something we have already done in week 1. Which means that if we know the sources, if we know the values of the latent variables, it's easy to estimate the parameters theta. And actually, if we don't have these hard assignments, but rather have soft assignments, so some posterior distribution on T, which means that for each data point, we don't assume that it belongs to just one cluster, but rather we assume that it belongs to all clusters simultaneously, all Gaussians simultaneously, but with some different probabilities being the posterior P of T given X and parameters. If we have these probabilities, it is also easy to estimate the parameters. So instead of just summing with respect to all blue points and averaging their position to get the location of the blue Gaussian, we'll have to sum all the points but with weights. So if the posterior P of T equals to 1 is 1 for some data point, it means that this particular data point is completely blue. It certainly belongs to the blue Gaussian, and it will be used as just, as blue data point in the averaging with weight 1. If for some data point P of T equal 1 is 0, it means that this data point is certainly orange, and we will just don't use it in the computing the blue Gaussian mean at all. But if the data point is like, for example, P of T equals 1 is 0.8, it just means that this data point is kind of not certain. It may be, it thinks that it belongs to the blue Gaussian, but it's not sure. And so it will highly affect the position of the blue Gaussian and a little bit affect the position of the orange Gaussian. So we will derive these kind of formulas later from more strict considerations, but now just believe me that if you know the posterior probability on T, you can easily estimate the parameters this way. Okay, but the bottom line here is that if we know the sources, no matter soft assignments or hard assignments, then we can easily estimate the parameters of our Gaussian mixture model. But on practice, we don't, right? We don't know the sources. So how can we estimate the sources? Well, it turns out that if we know the parameters, so the Gaussians, their locations and their variances, then we can easily estimate the sources, because we can use just the Bayes rule to do it. And by the Bayes rule, the soft assignment, the posterior probability of T equals to, for example, blue Gaussian, for some particular data point is just proportional to the joint probability, which is likelihood times prior. And if we know the parameters, theta, we can easily compute this likelihood and prior at any given point. So we can easily compute this posterior probability, which is basically sources, which is basically assignments for each data point for two clusters, soft assignments. You may think that the normalization constant here can be problematic, but it turns out that we have just two values here, so two probabilities. The distribution P of T given some data and theta can take just two possible values. So we can explicitly normalize this thing by summing with respect to two unnormalized probabilities. It's no big deal. Okay, to summarize, we have kind of a chicken and egg problem. If we know the Gaussian parameters, we can easily estimate the sources. If we know the sources, we can easily estimate the Gaussian parameters. So what can we do in this case? Well, the expectation maximization algorithm, in this particular case, suggests us to do a very natural thing. So let's first of all initialize the parameters somehow randomly. And then in iterations in the loop, let's repeat two steps until convergence. So first of all, let's fix the parameters, assume that they're the true ones, and estimate the sources. And on the next step, let's use these sources to re-estimate the parameters, to update our beliefs about the parameters. And this way, after repeating these two steps for long enough, we will hopefully obtain a reasonable solution to our probability distribution fitting problem. So we will be able to fit Gaussian mixture model into our data.